Empirical and molecular formulas. The goal of this video is to define empirical and molecular formula and learn how to determine both based on experimental concepts such as percent composition. The molecular formula gives the number and type of each atom within a molecule. An empirical formula, however, is always the lowest whole number ratio. You may recognize that for an ionic compound, these will be the same. However, for molecular compounds, they often are different. Let's take ethene as an example. This is made up of two carbons double bonded to each other, and each carbon has two hydrogens. This means that its molecular formula is C2H4, and its empirical formula is CH2. I put both the molecular mass and empirical mass alongside because I want to point out that those must always be a multiple of each other. We will use this in some of the problem-solving techniques later in the video. There are many ways in which to solve these problems are worded, and so we want to think of the problem-solving technique very holistically. In each case, your goal is to get to the lowest ratio of the moles of each atom, and so you must find the number of moles of each atom. If you are given the mass or volume of a particular atom, you can solve for moles by using simple conversion factors. Typically, it isn't that simple though. You will often be given a percent composition. If you are given percent composition, you will assume a 100 gram sample, and then each percent composition will tell you how many grams of each substance you have, which can be converted into moles using the molecular mass of the atom. Another way problems are often worded are to give you the amount of products found. You can use a variety of conversion factors and mole ratios to back calculate how much of each atom must have been present in the reactant. We will do a percent composition example in this class, and we'll do one given the reactants in class. Once you get the moles of each atom, we can do a math trick to get to the whole number ratio, or close enough that you could easily see the ratio. We will take the smallest of those numbers that we find of each atom and divide all of the moles by the smallest number. From here you can find the empirical formula. Let's do an example. Aspirin is comprised of 60% carbon, 4.48% hydrogen, and 35.52% oxygen, and I want you to find the empirical formula. First, we need to find moles of each atom. Now, for percent composition problems, we want to assume a 100 gram sample. This is because it makes our life simple. If we assume a 100 gram sample, we know that we would have 60 grams of carbon. So we take 60 grams of carbon and divide by 12.01 grams of carbon in order to get our moles of carbon. We can do the same thing for hydrogen. We have 4.48%. In this problem, assuming a 100 gram sample, that's 4.48 grams. We divide by our molar mass to get moles. Same thing for oxygen. 35.52 grams of oxygen divided by its molar mass gives us the moles of oxygen. Now, it may be difficult to get a whole number ratio from this. If you can see it, great, but for the rest of us, let's do our math trick. We find the smallest number, which is 2.20, and divide each of those by that smallest number. When we get this, we end up with 2.25, 2, and 1. Now, this isn't actually a whole number ratio yet. You can't just round down. However, it gives us the ability to see what we need to multiply everything by to get a whole number ratio. If we were to multiply this by 2, we still wouldn't have a whole number. But if we were to multiply it by 4, we would end up with a whole number here, here, and here. So let's do that. And we get C9H8O4. So that is our empirical formula. Now, oftentimes, a problem like this will be continued by saying, then find the molecular formula. If that is to be asked, some level of other information will need to be given. For instance, I tell you that the molecular mass of aspirin is 180 grams per mole, and I ask what the molecular mass of aspirin is. So we have some information from the previous slide. We know that this is our empirical formula. Now, in order to find what our molecular formula is, we need to know what we need to multiply the empirical formula by. Think back to that first slide when I discussed how the difference in, or the ratios of the masses must always be a whole number. So let's figure out our empirical mass. We look at our empirical mass and we notice something interesting. It's actually the same as our molecular mass. So our empirical mass, the mass of C9H8O4, is the same as our molecular mass. And if that's the case, we know that that's also our molecular formula. Now you know what molecular and empirical formulas are and have used one type of experimental data to solve for empirical or molecular formulas. This is only one of the types of questions that can be asked, and you should always be aware that your goal is first to find the amount of each atom present. But there are many different ways that are going to be required, all dealing with conversion factors. After you do that, you then solve for the lowest whole number ratio by first dividing by the lowest number and then looking to see if multiplying by a number is required. We will practice another more difficult question in class using the products of a reaction to solve for empirical formula instead.